Well, thank you everyone for being here. Thank you, Brent, for that introduction. My name is Terry. I am a PhD candidate at UC Berkeley. And today I'm going to be talking about some of the research that I've done with particles and turbulence. I've done this with my advisor, Evan Veriano at Berkeley, and then also with one of my advisors, Gauthier Verhil in France. And I know Zoom seminars all have their different kind of rules, but I think I'll be able to see the chat. So if you want to throw questions in there or like unmute yourself, I don't mind interruptions at all either. Great, so I want to start with a little bit of an outline so that we all have a roadmap of where we're going. I'm going to discuss some background and motivation for the work that I've done and try and relate it a lot to some different geological applications. Then I'm going to go into my two different projects. So as I mentioned, I study a lot of turbulence and trying to figure out how turbulence impacts the environment around it. And the things that I'm looking at right now are these little particles in this turbulent flow. And so first I'm going to look at how turbulence affects the movement of these particles, and then how turbulence affects how they dissolve or get smaller in time. And then I'm going to throw in a couple of geological applications at the end and discuss kind of where I want to take this research in the future. So the transport of particles in turbulence is an open question. We actually have some pictures from Michigan over here. Get the right laser pointer on. So this one is actually a picture that my sister took of this like frozen riverbed that has a whole bunch of sediment deposition on it. And then we have some pictures of like beachfront erosion here. And so part of what I can apply my research to is kind of looking at how particles are picked up and transported through the environment. So today I'll be focusing a lot on the different types of transport, and in the future I kind of want to expand them to like larger scale transports. And then another thing that I think is a really interesting kind of up and coming area of research is kind of reverse tracing sediment sources using mixing models. So a lot of sediment sources, I'm sure people in this department have done things with like chemical tracings, but there are a couple of new research avenues trying to figure out kind of what are some of these physical models and can we trace where those sediments come from, like for dust clouds and dust management through some more physical models. So here's a little bit of a preview. Let's see if this works. So this is a little bit of a preview of this motion particles that I was talking about. And so here we have these three different images of these flat particles, which you can see in my hand, and they've been reconstructed in 3 dimensions. And right now we're kind of just following the particles motion. So it's like spinning and tumbling from the particle point of view. And so hopefully by the end of this talk, I will have explained kind of how we get there and why this is important to our understanding of turbulence and how it interacts with the environment. And then the second half of the problem is that after we've looked at the rotation, we can then look at how the rotation influences how a particle will dissolve. And so this is really interesting for me because I'm trying to figure out, okay, does motion and surface area, do those actually influence this dissolution? Or if we had some types of sediment that were kind of like losing particles, would it dissolve, and kind of where would that dissolved mass go? Okay, so I've talked a lot about turbulence, and I want to just give a quick overview of what I mean by turbulence and some of the other characteristics and vocabulary that I'm going to be using throughout the talk. So if any of you have been in an airplane, you've probably heard the pilot say, like, buckle up, we're going to hit some turbulence. But like, what is this? It's this kind of chaotic flow pattern with universal properties, which means that if you were in one turbulent flow and you see another one, some of the properties will be the same between the two flows. And so that's kind of what one of the neat features is of this type of structures that I will be looking at. But how do we get turbulence? So these turbulent structures come from different types of fluid instabilities. And what does that mean? So if we look at fluid flowing from a sink, right here on this first panel, we can see something that looks laminar. So that means that these fluid streamlines that we have kind of follow the flow. They aren't like wiggling and waving and moving around. They're pretty straight. And then if we kind of open the sink a little bit more, we might have something that is transitional flow, which is this middle panel. And so this transitional flow starts with like a straight laminar portion normally, but then somehow it's bumped. So it's bumped and it's perturbed, and it ends up with this kind of unsteady portion here. So this unsteady portion is what we call an instability. And so this is kind of what the transitional flow looks like. But then if our instability becomes so big, we end up with this turbulent flow, which has all of these tiny eddies and swirls inside of it. So I will probably fall into using eddies as a habit, but I just mean different types of swirls and different size swirls as we go through the talk. However, underneath all of this is still kind of this background flow. So turbulence has this characteristic where you have all of these swirls on top of this kind of background flow. And so that's kind of just a general overview, hopefully a picture a little bit of what type of flow we're going to be talking about. Okay, so now that we have all of these different size swirls, like what does that mean? Do we care about those sizes? And for my research, yes, because some of those sizes, though each size has different properties. So one time I was explaining this to a postdoc in my lab, and I explained it in terms of Miss Frizzle and the Magic School Bus. And he didn't understand. And I was like, how have you never seen the Magic School Bus? But then we went through a couple of other examples. So here are the examples. If we start with something that is a really big scale turbulence. So let's say this is the largest scale that this particular flow that I've drawn has. But let's say that you're bigger than this larger scale. That means that everything here will just kind of feel like random noise to you. So let's say you're like walking down the street, you're this little dude in blue here, and somebody's like poking you. The poke isn't really gonna change your path. You're gonna kind of keep going, you're gonna keep doing what you're doing, and the poke is just gonna feel like a little bit of annoyance. So anything bigger than this larger scale of turbulence will kind of feel turbulence as a little bit of random noise, but it won't really change anything that that object is doing. If we look at the next scale, so we're looking at the smallest end, so we go all the way to the other side, anything smaller than the smallest scale will be a passive tracer. So this means that it will move however the flow moves. So how I picture this is that like, okay, I'm, sitting there or walking along and someone like comes by and runs and picks me up and knocks me over and carries me away. Like I can't do anything about that. I just have to kind of go with wherever that person is taking me. And so that's how passive tracers feel. Whatever type of flow or swirl is carrying them is kind of where they go. But then in the middle, we have this scale that kind of, might feel like a hug. So what happens here is that the properties of the object, so if we're continuing with the example, I would say the properties of myself kind of have the same type of force as the properties of the fluid that's around it. So on this scale, we really have to take into account kind of all of the forces that I have, plus all of the forces that the fluids have. And so when we have the big scale, it's like, okay, the fluid doesn't mean anything. When we're super small, we get carried away no matter what our inertia is. And then when we're kind of in this middle scale, it's like, okay, my properties matter and the fluid properties matter. And this middle scale is where I've done a lot of my research. But since it's difficult to model numerically because we have to take into account kind of both sides, I've done this mostly experimentally. So just to review this kind of first section, we have turbulence, which is hard to understand because it has all of these chaotic properties to it. And then we have this scale where we have to take into account both the properties of the object and the properties of the fluids. So these are the two things that kind of led me to investigate these experiments that I'm going to be talking about. Okay, so now we get to the first project. And this project looks at the rotation of these flat particles and is linked to that kind of first video with the 3 images in the reconstruction that I showed. So for this object, I really wanted to test how different shapes and different sizes influenced motion. So we're looking at how turbulence influences the motion of different particles through the environment. And so here I'm varying shape in this middle size, and then I'm varying size along this triangle shape. So when I put this in my flow, we get something that looks like this. We get these particles going everywhere. We're like, great, well, we can't really track with our eye how quickly they're spinning or they're tumbling or they're rotating. So how are we going to look at this and really get information from it that will tell us about the movement of these particles? Well, we did this with this setup, this experimental setup, this experimental turbulence tank. And if we look at it from above, we can see that it has these motors. So there's actually a motor on every corner of it. And then we have 2 cameras here. But we actually, if we look in 3D, we have 3 cameras. So this is the these are the 3 images that I showed before. And then motors, which aren't drawn on this 3D one. And in the middle, we have this turbulence flow. So an important note about the 2 experimental setups that I'm going to be talking about is that neither of them have that kind of background mean flow. So in order to simplify these experiments, I took out the mean flow. So we're just looking at the turbulence part. And then I also have particles whose densities are pretty close to that of water. So I don't have to look at gravitational effects either. And then to create this turbulence, we have these motors and they're rotating in alternating directions to make sure that we have kind of this no mean flow turbulence in the middle of the tank, which is where our experiments and our cameras can actually image. Okay, so now we've talked about the setup, but how do we get any information from these images? So if we look here, we can imagine that this is a camera 1 matching here. This is camera 3 at the bottom matching here. And this is camera 2 from the side. So if we were to fold this up, we'd have 3 sides of a cube. And so this is kind of what one of the images looks like that we're trying to reconstruct. So we're trying to figure out where these triangles are going in 3 dimensions so we can figure out how they're rotating and how that affects like where they may end up. So the first thing we have to do is identify a particle. So we're going to start with this one here in the upper left-hand corner. And then we have to figure out which particle in the other 2 images matches to it. So if we kind of project this particle from camera 2 onto camera 1 with these lines, so we're projecting that, we can figure out which particles match up to each other. And then we do the same for camera 3. And so we have these 2 that are matched here. However, we also see that there's another one in this kind of line between camera 1 and camera 3 that falls into this region. So we have this particle here and it's like, okay, well, are we sure that this one on camera 3 is the right one? And so what we do is we look and we say, oh, actually it was camera 2. There's a particle on camera 2 that matches with the 2 that we had on camera 1. So it's a little bit different. So maybe we have 2 options for this particular image. And to kind of figure out which option was the best, we would look at kind of this one, this match here, the first one that I showed in blue, the second match here that I showed in green, and then we would figure out from the 3rd camera which of these like lines are closest to each other. So they all look really close, but we can put in an optimization algorithm that actually computes how close these projections are. And then we take whichever projection is the closest. So whichever one between these 2 lines here matches closest to where we actually identify the outline of the triangle. Okay, so now we have our triangle. We figured out where it is in 3D. We have our particles, but we want to figure out how they move over time. And so in order to do that, we have to link them to what happened in the past. and what's going to happen in the future, right? So we have this particle in 3D and you're like, great, I have a particle 3D one-time step. How am I supposed to figure out how it changes in rotation, which will then tell me kind of where it may end up? Well, we do that by using something called the nearest neighbor method. And so if we look at this kind of diagram here, we see that these lines, these black dots, are particles that are already linked to a trajectory path. And these blue dots here are particles that have been identified in our next image. But we have a kind of restriction. So we have a search volume and we say, okay, only particles that are within a certain distance can be linked in the next image, because if not, it would have been too far away. We would be skipping something, we'd be missing some dynamics. So within this search volume, we have 2 particles and we choose the one that's closest. And that's how we create our trajectory path. Okay, so we've done our setup. We have identified our particles. We've created them in 3D. We've linked to the trajectory, but we still haven't figured out our rotation. And so what we do to that is we look at the evolution of the tumbling and spinning vectors. Okay, so what does that mean? What is tumbling? What is spinning? So I have this little card that my friend wrote me, and I'm going to try and use it as an example. So here we have a flat particle, and what we're looking at is the axis of symmetry. So here, if I were to take this particle and spin it here, then when 180 degrees, we'd have symmetry. And so we're going to call this like this is how we're going to identify symmetry. And so our axis of symmetry is going to be pointing out from it like that. And so this is going to be our z vector, which is on the screen here. So that's our z vector. It's coming out of the plane. It's coming and spinning around the z vector, which represents the axis of symmetry, is our spinning. So this is our spinning. And then the other 2, this one and this one, those represent our tumbling, because we're not going around our axis of symmetry. So by figuring out where the particle goes from time step 1 to 2 to 3 to 4, and looking at the evolution of the z vector as it changes, we can figure out our tumbling and our spinning. And so this is how we decompose our rotation to figure out if there is any type of difference in movement between the different shapes. So we did the same thing for all of the shapes. And if there's any type of difference between tumbling and spinning within these particles. So in the end, we end up with a plot that looks something like this for our different types of flat particles. On our vertical axis, we have our rate of spinning. So we have that kind of evolution of those vectors, or our rate of tumbling. So up here at the blue is our tumbling, at the bottom is our spinning. So it just depends on which vectors we're kind of looking at. And then at the bottom, we have our size. And so remember here, I have 3 different size particles. And then the symbols would represent our shape as well. So it's a little bit easier to see at the bottom, but there's a square here and there are some hexagons mixed in. But it's kind of hard to see the difference between the shapes, which means that the shape doesn't matter that much, right? If all of our shapes are overlapping and the line has collapsed on itself, then we can say, okay, shape doesn't affect this movement as much, but what we see here is that it's really our size. So as our size changes, our spinning rate changes as well. And so when we fit a line to this, we find a -4/3 power law scaling. So what does this mean? Why is this important? On the -4/3 power law scaling just means that we have those eddies of the same size. So we're back to this hug thing. We have those eddies of the same size that are the ones that are influencing the motion of the spinning and the tumbling of these particles. So when we're looking at this, we're saying that, okay, well, we really care about the eddies of the same size that dictate the movement, and that it's not the largest or the smallest ones. So this is what we expected. We expected particles to kind of behave based on eddies of their same size. We also saw that we have these flat particles that tend to tumble more than they spin. If you end up with something that looks like a rod, so a fiber does, like this is a fiber spinning here, right? So, and this is a fiber tumbling. So a fiber doesn't necessarily have the same characteristics of motion. So it's good to know kind of the geometry of the particle to decide if it's going to spin more than tumble or tumble more than spin. And then we also can say that these findings agree, this like -4/3 power law scaling agrees with some of these solid 3D particles, some of the chunkier ones, like the dissolving sugar ones, and some of the fibers. So we know that if the shape is like classified as one-dimensional, like a fiber, 2D, like these flat ones, or 3D, they all kind of follow this -4/3 power law scaling. Okay, so we got out of here. We're like, great. If we want to classify how much something's going to spin or tumble, how much, like what its rate is, we need to know the size of it, but we don't really care about the shape. That doesn't matter as much for the particle's movement. But then I talked about dissolving and dissolution. So how does that influence how particles loses mass through time? Well, we started with particles that were the same size because we had this results from these size experiments, and then we said, okay, what governs particle dissolution from the surface to the flow? Is it the size? I mean, we know that size governs motion and that they're the same, so their dissolution rate should be similar. But if we're doing kind of mass transfer, then maybe we also need to look at surface area. So like I mentioned before, we're doing neutrally buoyant particles. So I also had to make these kind of neutrally buoyant dissolving particles. I made them out of sugar, and it took probably over 100 tests. Thank goodness for the undergrads who helped me, because this was a lot of testing to do to actually find this recipe. And we ended up with this ideal sugar recipe that had a couple of key characteristics. So we needed particles that were pourable. We tried baking them in the oven, didn't work. We tried a couple of other cooking methods, and we decided that we really needed to be able to pour our mixture into our molds. We also needed these particles to be self-similar as they dissolve, which means that we needed them to keep the same shape. So they could get smaller, but we didn't want the shape to change, because if the shape changed, that would change our dynamics, and that would change. So we wanted them to kind of keep the same shape. And then we also wanted them to be neutrally buoyant so that we could get rid of this gravity. So in order to do that, I played around with a couple of different recipes, but what I found out was that we needed the two key parameters were this dextrose to sugar ratio, dextrose to sucrose ratio. And so dextrose is just a type of corn sugar, and sucrose is table sugar, and temperature. So I don't know if any of you have ever made caramel at home, but a lot of caramel recipes require table sugar and corn syrup. So corn syrup is like dextrose, we just use the powdered form. And then you have to heat it to a specific temperature. And so playing around with that, I had a couple of different recipes. So I had one, this one was pourable, but that's also because I didn't heat it high enough. So it was super crumbly. And then we had one where the temperature wasn't right. And so what happens is that sometimes if you heat it in the wrong way, it can become unstable. And so this is what happens here. And then eventually we found this middle recipe that had all of the qualities we wanted. And so an important note here is that in addition to this dextrose and this sucrose that I used, we also had these hollow glass spheres. And so these were teeny tiny 45 micron hollow glass spheres that we added into our sugar to make them neutrally buoyant. So my lab always smelled like caramel or burnt sugar, and people always wanted to eat it. And I said, please don't. It's been made in a basement lab and it has glass inside of it. So I don't know what that would do for you, but it's probably not healthy. After we had all of our ingredients and we figured out the perfect ratios and the recipes, it was time to cook it, which was probably the second hardest part. So we started out with our teeny tiny beaker. We added in our dextrose, our sucrose, our hollow glass spheres. We had a lot of them. And then water, because we needed to make it into a slurry and to mix it up. So then we used our stirring rod, mixed everything into a slurry, put on an insulating sleeve, and I'll talk about this, why we added this a little bit later, and added a thermometer. So what was important, as I mentioned before, is getting the temperature. So we really needed that thermometer. But a second way to get water content is to weigh it. And so when you're making candy on a stove, what a thermometer does is basically tell you the water content of your caramel mixture, because what boils off is the water. It's not your sugar. Your sugar's not going anywhere, but the water is evaporating. And so to kind of double check our mixtures, we looked at temperature and water content to make sure that our particles were really consistent from batch to batch. Okay, so we mixed everything up. We've gotten all our measurements. We heat it. Want to make sure we don't lose any heat. So here's our insulating sleeve. And we weigh it again, and eventually we find this kind of ideal water content. And so for us, it was between 5 to 6%. And so that could take anywhere between 20 and 40 minutes. A lot of times we did like a double batch, so we didn't have to make as many. And that took a little bit longer to cook. So we have this mixture, and then we had to pour it, which was kind of sketchy because the mixture would crystallize really quickly. And so we added this, that's what the insulation sleeve was for, also to make sure it didn't crystallize too quickly. So we poured these into our molds. And so here's one of my undergrads, Derek, pouring this into the mold. I made him pose for this. He's like, why are you making me do this? Obviously pre-COVID as well. But so we poured this into the molds. Here's an example of one of our rod molds that we have. And so we have this 3D printed negative mold, positive mold. We have this 3D printed positive mold and then this negative mold here. And so we pop out our particles from the silicone once they're all hardened. And then we get these particles here. This is what they look like in the end. And they lie within this inertial subrange of turbulence, which is kind of this hugging scale that I talked about before. So in the flow that we used, which I'll discuss in a couple of slides, the kind of medium-sized eddies that we have were the same size as these particles that we created. And so that was our goal, is to kind of look, okay, if we can model everything else numerically, the small ones and the large ones, let's really try to do experimentally these medium-sized ones. Okay, so we finally gotten to this shape thing, this shape result that we talked about in the first project. We finally have these two particles, this rod and this disc. They're neutrally buoyant. They're self-similar as they dissolve. They have the same volume. So we're going to take volume as an indicator of shape for this project. So they have the same volume, but they have different surface areas. We're like, great, with the same volume, we know that they should dissolve, or they should interact with the flow in the same way. But with different surface areas, we don't know how much they'll dissolve. So this tank that we had was much different and a little bit gentler. The sugar particles would have broken if they hit the impellers of the other tank. So here instead we used these jet arrays. So there are 120 jets in total, and they're randomly turned on and fired to kind of make this turbulence in the middle here, where we can see our particle and our axis of our tanks. So we put the particle in, we kind of let it move around for a little bit in the flow, and then we take it out and we weigh it, and we figure out what our mass change is over time. Okay, so move my face. So if we look at the particle dissolving over time, we can see that at the start, hopefully it will start again. So at the start, we have this kind of very fast movement, and then at the end it kind of slows down and it stays in one place for a while. And so this is what this looks like a little bit. So we have the particles dropped in here. The video starts at 0 seconds. It moves pretty quickly for about 2 seconds, and then it stays in one place for about 4 seconds. So this is kind of a little snapshot of what we saw a lot of when we were doing our measurements. A lot of the particles kind of moving fast if they kind of felt these like big swirls that came in, or kind of staying in one place for a long time if they felt kind of these like medium-sized swirls. So now we have to create a model. So how do we even create a model for these things that are dissolving? Well, we did kind of a simplified model based on the volume of the particle, because we have this ratio between volume and mass using density. And since we have a density of the fluid and a density of the particle that's pretty similar, we can directly relate our mass and our volume. So we're making an assumption that we have a constant recession velocity, KT, which means that each side of the particle loses the same amount of length. So our L naught gets shorter and our H naught gets shorter and our W naught gets shorter by the same amount each time step. So here we have an example. This dashed line is the same size as kind of this initial one. And then here we have our change in L, our change in W, and our change in H over time. And so we see that our particles shrinking as they get smaller or as time goes on, but they're kind of keeping the same overall shape. So using this relationship, we can create a simple change in volume model. So we say, okay, our change in volume, which is our dl, dw, dh, is equal to our initial length minus our recession velocity times whatever time it has been since we started. And so this will give us, again, a value of length. And then we do the same thing for width and height. And so when we have this type of model, we can calculate our volume from our mass. When we took out the particles and measured them with mass, we can figure that out. And then we can fit our data to find K, which is what we're interested in because our recession velocity is then our dissolution rate. Okay, so the results of my experiment look something like this. They're also still in progress. So on this vertical axis here, we have our mass, which is normalized by our initial mass. And on this horizontal axis, we have our time. So here we have that these disc-shaped particles that I showed are in the blue stars, and they dissolve slower than the rod-shaped particles, which are in the green here. And so this is also kind of to be expected because they both have the same volume, so they have the same motion, but these rod-shaped particles have a smaller surface area. So we're saying, okay, great. So what we thought, what we predicted would happen, happened. It's our surface area that kind of governs our dissolution rate. So what happens if we have the same surface area? That I'm still working on. I'm analyzing the data right now, so hopefully we'll get that to you all soon. But yeah, so we end up with these things saying, okay, well, we've proved that, so we end up with, from that graph, we can say we've proved that it's not only volume that governs dissolution. And so a couple of reasons why we thought this were like, okay, if, volume governs motion and neither of the particles are moving as much or something, then like maybe it also governs dissolution. But in fact, that's not the case. And so we know that surface area has to play a role. So our next question are, do surface area and volume interact? Is it just surface area that governs it and not volume? So even though we know volume governs size and size governs motion, is it surface area that kind of like is a bigger order of magnitude that influences dissolution, and so like size and motion don't matter anymore? Or do those two kind of interact as they dissolve? And so this is one of the questions that I'm trying to answer in the next few months. Okay, so now that we've kind of got this story of our particle movement and our particles getting smaller over time, there are a couple of questions that I'd like to ask in the next several years as I keep doing research. And some of those have to do kind of with how do these two kind of play on each other more. So one of them is that I've been looking a lot at particles that are single. So I've looked at one single trajectory or one single particle, but you don't often find that in nature. You often find these particles that are grouped together, that are in some type of plumes or that are interacting with each other. And so one of those That's one of the questions that I want to address, which would also kind of tie back into this like dust particle motion. So I know the motion of a single particle, but if there are more, if they're kind of moving together, would that make their like friction from the air, from the fluid less? And so would they move faster? And so that's one of the questions that I kind of want to answer. And also, like, if we had multiple particles dissolving, then there would be some types of concentration gradients, some concentrations of sugar or of whatever is dissolving that would kind of play into account for those dissolution rates as well. And then another picture from my parents' land, but with our dogs over here. So landscape. So we were talking about kind of that landscape evolution, and I tried to find some pictures from when I was a kid in this like same spot, because I love this spot in the river. So I know I take pictures of it almost every year, but this is all I could find. But I'm kind of interested in saying, okay, what happens over time? We know all of this information about turbulence, but how does that kind of like, how do those dynamics change? Can we track kind of, I know there's a lot of research that has been done kind of on like where particles get picked up and put down, but can we kind of track that backwards? I think that would be cool too, if we, you know, kind of don't have the flow history of the river. Can we, you know, model maybe the particles or something going backwards based on the current flow statistics of the water? And then, of course, most things can be tied to climate modeling. So this is also another really good application, especially if we're looking at kind of either like volcanic emissions and kind of how they're reflecting solar radiation, where they're traveling. In California, we had huge fires the past 3 years, and which could be seen kind of all over the world, and getting smoke, you know, all the way over on the East Coast. So really kind of modeling those particulate clouds is also super important for health and just like climate in general. So before I finish, I want to thank all of my undergrads who helped me and my advisors. So here are both of my advisors, one from Berkeley, Professor Variano, and my advisor in France, Dr. Verheul, and then my 4 undergrads who have worked with me in this basically anywhere between 3 months in the summer to, I think one worked like 2.5 years. And so without them, I definitely couldn't have done this research. And then everybody in my group at Berkeley and our funding sources. So with that, thank you.